In this example problem, we'll be looking at heating up something with friction, effectively. This is a way of looking at different types of energy changes than you typically do. So we're going to look at the case of dropping a rock into a pond, and that process then heating up the water. Now, as you might suggest from the fact that it's called inefficient water heating, it's not going to raise the temperature of the pond very much at all. Um, and so one of the ideas here is to compare the scale of normal sort of mechanical energy changes, 3 kilogram rock lifted up, 3 feet or so, which is about a meter, versus, medium-sized pond, and how much does in the course of a day it might warm up and down a little bit. How does that sort of energy change? They're kind of converting the degrees Celsius of a certain volume of water into a certain amount of energy. Get a sense of the scales here. So let's talk about how we'll approach this problem, and let's draw this problem. So initially, I'm going to have a pond whose volume is 10 cubic meters. I'm going to have a rock with a mass of 3 kilograms, and it's going to fall down a distance of 1 meter into the pond. The idea here is that as the rock drops, it loses gravitational potential energy. That picks up as kinetic energy going faster and faster, hits into the water, and comes to a stop. Where does the energy go? Well, it goes into the internal energy of the water. So at the end, when the rock is at the bottom, you can have a slightly increased temperature because the internal energy is larger. So we want to consider the change in temperature. So this is the initial temperature. What is the final temperature? And what is the difference in temperature? So find the change in temperature. Now, the way we would think about this is how much energy do you lose as you drop down 1 meter? We just want to know the magnitude of that. I'm going to call this distance h. Then it's just mgh. That's the amount of energy you lose. Where does it go into? It goes into heating up water, and the amount of energy, the amount you increase the temperature is related to mc delta T. That's the formula that relates how much energy goes into internal energy as heat, and how much that then turns into a temperature change. Now, this looks a little confusing because it looks like you could cancel out the m's. But remember, these are different m's. This is the mass of the rock here, so I'll call that m sub r. And then this is the mass that's warming up, in this case, the water of the pond. So what's the mass of the pond? Well, the mass of the pond, assuming it's all water, is the density of water times its volume. So plugging that in, I get the density of water times the specific heat of water as a liquid times the change in temperature times the volume is the mass of the rock times g times h. To find the temperature change, all I have to do is divide over. So I'm going to the mass of the rock times g times h all over the density of water, the volume of the pond, the specific heat, no, this is a C here, specific heat of water as a liquid. I'll multiply, these are the 3 terms here, and those are all what's in the denominator. If I plug in my numbers, the rock has a mass of 3 kilograms, g is 9.8 meters per second squared, the height change is 1 meter, the density of water is 1,000. Remember, this is in kilograms per cubic meter, the SI units that we'll want, not 1, which is grams per milliliter, if you might be familiar with that from chemistry. The volume is 10 cubic meters, and the specific heat is 4,180 joules per kilogram Kelvin. Now, if you plug all of that in, you're going to get a really small number, because the numerator is about 30, and look, you get about 10,000 times 40,000, so 4,000, so it's going to be really quite small. Specifically, it's 7 times 10 to the negative 6, like 7.0 to more significant figures. 7.0 times 10 to the negative 6 degrees Celsius, which is the same thing, by the way, as in Kelvin, because this is a temperature change. So the short of it is you wouldn't notice this heat change at all. And in fact, the amount of energy that goes into a pool is much, much smaller than the amount of internal energy that comes in and out, just due to warm air blowing over it, giving heat into it. So this mechanical work, that amount of energy is way smaller than just kind of ambient heat flows out of it, because it produces an extremely small change in the temperature of this object.